之後，而家要面對另一個同樣基本嘅問題。
If the universe has a beginning, if it was born, does that then mean it'll eventually die? Or keep on going forever, eternal? You see, for us, as all too mortal humans, the ultimate fate of the universe is a question that's hardwired into our psyche. Trying to answer it has driven an astonishing revolution in our understanding of the cosmos.
不過近年，我哋亦都發現宇宙原來比我哋想象嘅離奇古怪得多。呢啲都係科學史上最令人震驚嘅時刻。超過100年前發生嘅事，可以話係峰迴路轉。因為好多關鍵實驗同研究都係由嗰陣開始。
And there it is. Exactly where Hoyle predicted.
佢引領我哋更接近去揭示宇宙終極命運嘅答案。宇宙真係大到令人冇辦法想像。究竟點先可以知道咁龐大、咁複雜，比我哋大咁多嘅系統，最後會點樣終結呢？自從我哋開始諗到呢個問題嗰陣，答案就全憑一個簡單嘅意念去推敲。
If we could chart, observe, and understand how the universe has changed, how it has evolved to the present moment from its very ancient beginnings, then we should be able to extrapolate it forward and predict how it will evolve in the future. Unfortunately, the slight flaw in that plan is that the universe operates on timescales of millions and billions of years. We don't.
要了解宇宙嘅運作，我哋就要用更長時間做量度單位。喺呢個情況下，龐大嘅宇宙反而對我哋有利。正因為宇宙有咁大，我哋喺夜空見到嘅星光，要花成幾百萬以至幾十億年時間先至傳到嚟地球。我哋仰望長空，見到嘅都係宇宙漫長嘅歷史記錄。
The problem is we only have a snapshot, a single complex and confusing picture of all this history. It's like taking all the words in a novel, jumbling them up and sticking them on a single page. The key is to try and unpick this story, to learn how to read it, to recognize and understand what's going on.
天文學家發現行星可以幫忙解開呢個答案。
If scientists could work out how stars change, how they evolve in time, they could begin to understand the bigger story of how the universe was changing, the first clues to what the future might hold.
不過要等到20世紀中期，我哋先至揾到答案。
Unlocking the secrets of the stars would take a moment of brilliance from this man, Fred Hoyle. Hoyle was a brilliant mathematician and physicist, one of the greatest of his day. He was creative, coming up with bold theories. Above all, he loved a problem, some thorny issue he could make his mark by solving. And in the late 1940s, he found one of the biggest.
霍伊爾想知道元素嘅來源。 宇宙主要由氫同氦組成，係最簡單又最輕嘅元素。但係我哋知道後嚟亦都改變咗。
Look around us now. This is no simple world we live in. We're surrounded by complexity, built from complex, heavy elements like the oxygen I breathe and the iron in our blood, and of course carbon in the trees and in every cell in my body. No one knew how to bridge the gap, how the universe went from that very simple beginning to all of this. This was the problem Hoyle seized on.
霍伊爾知道個答案一定同核聚變有關。喺核聚變入面，比較輕嘅元素融合埋一齊，形成比較複雜嘅元素。我哋知道行星核心會出現呢個情況，氫融合埋一齊形成比較複雜嘅氦。霍伊爾之後發現行星最後亦都會有耗盡燃料嘅一刻。而由行星嘅演化，我哋可以窺視宇宙嘅未來。呢個就係推斷未來發展嘅基礎。
It was hydrogen and helium that first formed stars, and it was these two elements that were consumed in stars as they aged, creating all the heavier elements in the process. The logical conclusion was disturbing. After an almost unimaginable length of time, stars would use up all the hydrogen and helium in existence. No new stars could form, and existing stars would eventually run out of their fuel and die. The universe would go dark.
根據霍伊爾嘅理論，由行星創造出嚟嘅光同生命會消失，宇宙最終會終結。不過仲有一個選擇，一個可能會有完全唔同命運嘅選擇，而且喺行星耗盡燃料之前就會發生。呢個選擇涉及宇宙一種基本嘅力量——重力。
The potential for gravity to define the ultimate fate of the universe was first spotted by one of science's unsung heroes, Vesto Slipher. Little known, his pioneering expert measurements would transform our understanding of the universe.
喺1900年代初期，天文學進入黃金時代，以有史以嚟最強力嘅望遠鏡對準天空。當時最大嘅目標就係星雲。
Nebulae were patches and swirls of light that could be seen in between the stars, and not much was known about these mysterious objects, so astronomers were scrambling to find out as much about them as possible. Slipher was interested in one particular aspect of nebulae, their motion, and for his target, he chose the most famous one of all, Andromeda.
斯利弗想成為第一個量度到星雲移動得有幾快嘅人。問題係佢個望遠鏡並唔係當時最強㗎，而且仲差好遠。不過斯利弗比對手有一個好大嘅優勢，佢係一個好傑出嘅天文學家。
This telescope is actually the same size as Slipher's. It has a 24-inch mirror. But Slipher would have loved to have got his hands on something like this. You see, what he needed was to get a spectrum. Now, that involves splitting the light from the nebulae into its different wavelengths, the different colours that it's made of. Now, he'd have used something like this. It's a diffraction grating. I can see it reflects this light and gives me all the different colours of the rainbow. What worried Slifer was that he needed to collect as much light as possible to give him a usable spectrum, and nebulae are exceptionally faint. He feared that getting enough light from his telescope would prove to be impossible.
雖然大細一樣，但係呢個現代望遠鏡可以喺幾分鐘內就捕捉到仙女座嘅光譜。而斯里弗當時用嘅望遠鏡就足足需要14個鐘頭先至取得光譜，足足辛苦2日，每晚花7個鐘頭不停調校望遠鏡，令到焦點對準仙女座。
Slifer wanted to know how Andromeda was moving, and for that he didn't just need the spectrum of light from Andromeda, he needed to have the absorption lines. Now these are discrete gaps in the spectrum, like this. Now these absorption lines should always be in the same place if the source isn't moving. If they've shifted to the right towards the red end of the spectrum, that means the source is moving away from us. If they've shifted to the left towards the blue end of the spectrum, that means the source is moving towards us, a blue shift. Now, after 2 days of observing, Slifer was ready to develop his photograph. And he didn't get something as beautiful and clean as this. He got this image. Now, this is in fact blown up. In fact, what he got was a much smaller image than this. And it's not even these lines, top and bottom. In fact, what he got was this dirty smudge in the middle. That was the spectrum from Andromeda. Now, you might think he'd failed, that you couldn't get anything meaningful from this. In fact, not only was he able to get a meaningful measurement, he could work out that Andromeda showed a very clear blue shift, that it was moving towards us. In fact, he worked out it was moving towards us at a speed of 300 kilometers per second, which actually matches modern-day estimates.
斯里弗成功啦！第一次量度到星雲嘅速度，佢嘅技巧同堅持克服咗喺望遠鏡硬件上嘅局限。
When Slifer presented his findings at an astronomy meeting in 1914, he received a standing ovation. It's often easy to forget how important people like Slifer are. The major breakthroughs in science aren't always about the big idea or the beautiful theory. They're often simply reliant on people who are exceptionally skilled at observing and measuring the natural world.
而家我哋知道仙女座星雲其實係一個銀河，就好似地球嘅銀河一樣。而且仙女座嘅移動可以揭示重力可以點樣影響宇宙嘅命運。自從大爆炸令宇宙誕生之後，宇宙就一直向外擴大，結果大部分銀河互相遠離。銀河最初形成嗰陣，仙女座同地球嘅銀河都一樣，直至重力發揮作用，開始抗衡膨脹。
It's gravity that's dragging Andromeda and our own Milky Way galaxy inexorably together. The question is, if it can pull off this trick in our own little corner of the cosmos, can it do the same over the entire expanse of the universe?
If 重力可以抗衡膨脹，咁喺行星死亡之前，我哋嘅宇宙就一定無可避免咁自我崩壞。宇宙會隨之死亡。如果冇重力，宇宙就可以一直膨脹， 比上一顆行星死亡嗰陣擴大得更遠。一切就視乎愛因斯坦相對論所預測嘅一個因素。
Using general relativity revealed that there were two very different futures to the universe. What's more, they were able to calculate a specific figure that marked the boundary between these two different scenarios. It became known as the critical density.
臨界密度其實就係一個門檻，建基於有幾多物質同能量，整個宇宙入面有幾多嘢。如果總數比臨界密度高，咁重力就會將成個宇宙再拉埋一齊。如果總數少於臨界密度，咁宇宙就會繼續擴張落去，直到永遠。
The fate of the entire universe came down to a simple question. What universe do we live in? One that is above the critical density or one that is below?
有咗明確目標，但係我哋究竟要點樣先至可以測定宇宙有幾咁接近臨界密度，嚟繼續推斷宇宙唔會自毀，抑或會繼續膨脹？當時有另一個選擇，一個好直接嘅方法。
One obvious way to see how close the universe is to the critical density is just to count how much stuff there is out there. It's a simple enough idea, but rather difficult to pull off. After all, in something as almost unimaginably vast as the universe, how do you count every galaxy, every star, every speck of interstellar gas? It's almost impossible.
所以天文學家乾脆將宇宙縮細。佢哋點算一個細嘅範圍，然後再乘以幾多倍。佢哋之所以可以咁做，全靠宇宙一個好特別嘅情況。
As far as we can tell, the universe is, on the larger scales, the same in whatever direction we look. So, an astronomer sitting here on Earth looking out into space will get pretty much the same view as an alien astronomer on a planet thousands of light years away looking out in a completely different direction. And that's why measuring how much stuff there is in one small part of the universe gives us a pretty accurate measure of how much there is overall.
佢哋點算到一個平均數，然後得出宇宙質量同能量嘅一個總數。
The results took everyone by surprise. All of them suggested the universe was well below the critical density. In fact, the best estimates suggested the universe had so little mass that its density was only a tiny fraction of the critical value.
好明顯，如果係正確嘅話，宇宙就絕對冇可能會崩塌。不過，宇宙有幾接近臨界密度嘅第一個估計有一個問題，因為個數字低到根本唔合理。
A flat white coffee, please. Ours is so clearly a universe of matter, mass and energy. They dominate our world. They are our world. These findings painted a picture of a universe so alien to our everyday experience that it's perhaps understandable it was such a difficult concept to embrace.
更重要嘅係，個估計好似同宇宙格格不入咁。哈佛大學嘅馬格麗特蓋勒以史無前例嘅規模繪畫出宇宙，就顯示出唔吻合嘅程度有幾大。
What Geller and her team did was first take a slice of the universe, some 500 million light years long, 300 million light years wide, but still a thin wedge of the visible universe. They observed as many galaxies as they could and plotted them against distance. So every one of these dots is an individual galaxy. There's over 1,000 of them. What took everyone by surprise was this pattern that they saw, these bubbles or almost a honeycomb structure. You see, everyone had assumed that the galaxies would be scattered randomly throughout the universe. Here, for the first time, was evidence that, far from random, the universe actually had structure.
喺呢個新發現嘅結構中央，就有重力存在。
Since almost the beginning of the universe, gravity has been drawing matter together. First, into clouds of gas, which then clump together to form galaxies. These galaxies come together to form clusters of galaxies, and the clusters into superclusters. It's like a work of art. These superclusters of galaxies are all joined together by filaments of dust and gas, all acting under the same irresistible pull. my universe has just collapsed. Here we clearly see gravity acting as an architect, shaping and influencing the structure of the entire universe on a truly cosmic scale. No, I think I can do better.
問題係宇宙入面估計嘅物質好細小，
Let's open that up.
令到宇宙處於能界密度之下好多，所以呢個龐大結構根本冇辦法形成。
I don't like that.
根據呢啲數字，我哋所認知嘅宇宙係冇可能存在㗎。
This is a rubbish universe.
計算期間一定漏咗一啲重要元素，不過漏咗啲乜嘢呢？而呢個遺漏對臨界密度同宇宙嘅命運又有乜嘢意義？20世紀最矚目而且最具爭議嘅科學家之一，就揾到第一個線索，佢係弗里茨智威基。
Zwicky was an eccentric, abrasive, and brilliant scientist, known occasionally to refer to the rest of his profession as spherical bastards, which is basically anyone who's a bastard whichever way you look at him. But even those who disliked him had to admit that he was capable of brilliant work.
當時佢亦都正係研究星系結構，發現到一啲不可思議嘅現象。
This picture here is just such a galaxy cluster. It's called Able 1689. Each one of these yellow dots is part of the cluster. It's quite incredible to think that each one of them is an entire galaxy in itself. It sort of gives you an impression of the sheer scale of these things.
智威基覺得嗰啲可以將星系團黐埋一齊嘅力量好神奇。
The answer, of course, has to be gravity. Imagine these marbles are all each individual galaxies, moving in chaotic orbits around the center of the cluster. But none of them moves fast enough to be able to break free and escape from the cluster.
因為咁，智慧機就可以利用佢哋嘅移動速度去量度固定星系位置嘅重力，然後透過重力力量知道星系團入面有幾多物質，有幾多元素。好奇怪嘅事就喺呢度發生咗，原因係銀河嘅移動速度非常快。
The strength of gravity needed to hold all these speeding galaxies within the cluster required far more mass than he could see. And it wasn't just a small difference. In fact, he needed something like 100 times more mass than could be detected.
智慧機叫呢個神秘質量做暗物質，亦都係宇宙失去質量嘅罪魁禍首。不過要知道佢令宇宙處於臨界密度之上抑或之下，就要先解決一個重大問題：點先可以研究到一種至今未有方法偵測嘅神秘物質？
The answer would come thanks to a discovery made here at the Jodrell Bank Observatory. This giant dish is the Bernard Lovell Radio Telescope, and in 1973 it spotted something no one had ever seen before.
"當時佢哋觀測緊宇宙入面一種好遙遠、好光嘅星系，稱為類星體。當觀察到一半嗰陣，佢哋偵測到一種好特別嘅現象。我今日就嚟睇下佢哋當日遇到嘅情況。不過就唔單止會用天文台嘅望遠鏡，仲有全英國各地嘅射電望遠鏡。
Right, here we are, the control room at Jodrell Bank. A lovely view there of the Lovell telescope. Now, over here, on these screens, we see live data coming in from various telescopes. One of them, the Mark II, is a radio telescope here at Jodrell Bank, but the rest are scattered around the country, all linked together through optical fibres feeding into the central computer here. Now, the point is, the longer you observe an object, the better quality image you get. And after 50 hours of observation, here's what they see. This is the same image as was seen 40 years ago, showing these two bright dots, two quasars. Now, this wasn't the first time quasars had been seen, but certainly the first time they'd been spotted so close together, as though they were a pair.
一對咁樣出現真係第一次見，於是佢哋着手收集盡量多嘅資料，包括量度兩個類星體嘅光譜，即係光所含嘅獨特指紋。
Here are the spectra from the two quasars. Now, even at first glance, I can tell they look quite similar. In fact, they're much more than just quite similar. When they first measured them, they saw that they were both redshifted to longer wavelengths by exactly the same amount. And have a look at these emission peaks here. They both fall at exactly the same wavelengths. In fact, the spectra were so similar, they thought they'd made a mistake, that they'd looked at the same object twice. But they hadn't. And that left just one possibility. What they thought were two separate quasars were in fact just one single quasar that had somehow been split into two images. A case of astronomical double vision.
有一個理論可以解釋到呢個情況。愛因斯坦預測嘅一個奇怪效應——重力透鏡效應。
If you look through this lens, you see that everything behind it is warped into strange shapes. This bizarre effect is because as light passes through different thicknesses of the glass, it bends, giving rise to a warped image. Now, Einstein said that matter, stuff, also warps space, changing the very shape, the fabric of the universe. And so, as light passes through regions of space with high concentrations of matter, it will bend, just like it does going through the glass of this lens, and so giving rise to similar visual tricks.
有幾多光線被扭曲，視乎太空嘅變形程度。而呢個又要睇太空嗰個地區有幾多物質。喺類星體同望遠鏡之間，一定有好大量物質，令到光線嚴重扭曲，以致將影像分裂。咁一個類星體就好似變成兩個咁樣。
Here's our culprit, or at least part part of it. This smudge here is just one galaxy within a cluster of galaxies that sit between us and the distant quasar. So it's not just a little bit of mass, but hundreds of galaxies, each with billions of stars. Combined, they bend the light from the quasar, giving us the double image.
重影對研究暗物質好重要。就算星系團入面所有質量同物質都唔足以令到光線扭曲得咁嚴重，所以智慧機所講嘅神秘暗物質就大派用場。小心分析有幾多光線被扭曲，就可以查出暗物質所在位置。
This is what you get, a map. In the center is the normal matter of the galaxy cluster itself, but surrounding it, stretching out much further, coloured here in red, is the dark matter. Look how far out it spreads. It completely dwarfs the normal matter of the galaxy cluster. Zwicky's mysterious and invisible matter revealed by a cosmic optical illusion.
雖然咁樣揭示唔到暗物質究竟係啲乜，不過天文台至今仍然繼續繪圖，等我哋知道暗物質大約有幾多。睇嚟比正常物質多好多。但係咪足以令到宇宙超出臨界密度呢？
Even though there appeared to be far more dark matter than normal matter, that still seemed to leave the universe way below the critical density. But this was still far from the end of the story. The discovery of dark matter had taken the scientific community completely by surprise. Trying to work out how close the universe was to the critical density was just throwing up more mysteries than answers.
一個令人震驚嘅新發現，最初好似終於揭示到宇宙嘅命運，不過反而令到物理學陷入危機。1990年代，科學家組織咗一項國際計劃，利用望遠鏡追尋宇宙命運嘅答案。佢哋利用新技術，研究宇宙擴張點樣隨時間而起變化。而家就用呢個巨型望遠鏡去觀測宇宙核心嘅星體。
This huge telescope, you can see the vast mirror behind it, is going to take a close look at a supernova, the explosive death of a star. The light reaching us from these distant epic events would be key to unlocking how the universe expanded in the past, and in turn would reveal what would happen to it in the future.
要量度宇宙膨脹，研究人員對某類超新星最感興趣。
Our target tonight is the same class of supernovae that they were searching for, a Type 1a. Now, what made Type 1a supernovae so useful is that when they went off, they created an incredibly bright spike of light. Briefly, the star would shine brighter than its entire galaxy. Not only that, but they always gave off almost exactly the same level of brightness. This meant that not only could they see them over vast distances in remote galaxies, but they could also work out exactly how far away they were. So, if they could find enough of them, they could sample conditions in the universe over a wide range of distances and times.
今晚天文學家艾凡斯正係尋找一顆新近發現嘅1A 超新星。
Right, David, this is very exciting. Do you have the supernova?
This is the image of the supernova.
That thing there?
That thing there.
Can you zoom in at all on it?
Yeah, we can zoom in here, and you can see the bright dot.
And that the rest of it is the galaxy.
The rest of the light you can see there is the host galaxy of the supernova.
I mean, that's incredible. Here's a galaxy with hundreds of billions of stars, but this one exploding star, this one supernova is shining brighter than the whole of the rest of the galaxy. And you know how far away this supernova is. You've measured the distance.
Yeah, the supernova is about 8 billion light years away.
Wow.
除咗距離，超新星嘅光譜亦都非常重要。
The astronomers needed the spectrum of the light because it gave them the redshift. You see, as the light travels from the distant supernova to Earth, the universe is expanding. The space the light is traveling through is stretching, and so the light itself is also stretching. Its wavelength is getting longer. If it leaves the supernova at a particular wavelength, a particular color, when it arrives in our telescopes, it's at a longer wavelength. It's shifted towards the red end of the spectrum, hence a redshift. So knowing the redshift of the light tells us how much space has expanded in that time. In a sense, it gives us a measure of how big the universe has become.
因為咁，量度遠距離嘅紅移喺好耐以前可以構建出宇宙擴張嘅轉變歷史。天文學家深信重力至少減慢咗擴張嘅速度，問題係減少咗幾多？透過量度宇宙擴張同紅移所得出嘅距離，佢哋終於回答到呢個問題。
Now, if we imagine the universe has been expanding at the same rate, the rate that it is now for its entire history, I'd get a very simple line. But astronomers knew this couldn't be correct because, of course, gravity is putting the brakes on the expansion. So the expansion of the universe should be slowing down, and if it's expanding more slowly now, it should have been expanding more quickly in the past. Space stretching more would mean a bigger redshift. Now, what does this mean for our supernova? Well, we know it was 8 billion light years away. So we know it wouldn't fall exactly on this line, which corresponds to a redshift of about 0.49. It should sit maybe somewhere over here, maybe at a redshift greater than 0.5. That means this line should really be curving down like that. But of course, the exact shape of this line would tell them how much gravity is slowing down the expansion of the universe. And that would tell them the fate of the universe. Okay, so David, you have the spectrum ready now.
We have it. Let's bring it up.
And that gives you a measure of the redshift. So what did you measure that to be here?
For this case, we measure 0.47.
0.47, well, that puts it on this side of the line. That means it's not a larger redshift, but a smaller redshift. This is fascinating because it's exactly what they saw. Not redshifts that were larger, but redshifts that were smaller. And they saw this time and time again, and it could only have one explanation. Smaller redshifts meant that the universe must have been expanding more slowly in the past than it is today. In other words, rather than slowing down, the rate of expansion of the universe is accelerating.
當被記低嘅超新星越嚟越多，成個畫面亦都更清晰。宇宙大爆炸發生後嘅頭幾十億年，擴張速度似乎符合預期咁慢。不過後嚟唔同咗，膨脹速度開始加快。
It's hard to stress how much of a shock this was. Back then, everyone knew that the expansion of the universe had to be slowing down. Now, whether it would slow down enough to stop and then recollapse, that wasn't clear. But it had to be slowing down. After all, gravity had to be doing its job of putting the brakes on. But it wasn't. About 6 billion years ago, the expansion started to speed up. Clearly, there was some new and unexpected thing going on in the universe, something that science didn't have an answer for, something that was pushing the expansion of the universe at an accelerating rate. It became known, for want of another term, as dark energy.
目前最準確嘅估計係暗能量佔宇宙嘅70%，咁代表宇宙唔會突然崩塌，亦都意味係暗能量而唔係重力決定宇宙嘅最終命運。
Dark energy pushes the universe apart. It won't carry on expanding steadily forever. Instead, dark energy forces the universe to fly apart at an ever-increasing rate. Galaxies will become so far apart that light wouldn't be able to travel between them. Each one will end up as an individual island of stars alone in the cosmos. It may even become so extreme that galaxies themselves will be ripped apart, leaving individual stars all alone in the black emptiness.
又或者唔會係咁。喺60至70億年前之間，暗能量突然出現所帶嚟嘅各種影響。邊個講得準暗能量未來會點？聽落嚟或者好奇怪，但係發現暗能量一切都要從頭再諗過。
It's hard to stress how little we know about dark energy. It has a name, but that's about it. We don't know what it's made of, why it's driving the universe apart, and crucially, how it'll behave in the future. And that leaves a big hole in our understanding of the universe and its ultimate fate.
暗能量可能只係整個宇宙運作嘅一部分。不過喺最重要而可靠嘅科學理論下，呢一個可能正係我哋去理解宇宙運作嘅最根本問題。
How the universe will end started as astronomy's great challenge, but the fate of the universe has become much more than just an academic question. Through the discovery of this strange enigmatic energy, if indeed that's what it is, one that defies current understanding, it spread to the heart of fundamental physics. Finding the answer to how the universe will end could have profound implications on how we understand our world.